question?
Yeah, sure.
Like on this one,
I think you've got about 30 seconds or so.
okay. So like on this one here, when I was solving it, I plug it back into U to find my new limits of integration. And I guess I'm confused. What how was I done? If I put 0 into e to the x, I got 1.
Yeah,
And
but the only issue with the comment here is that tangent inverse 1 comes out as pi over 4.
oh, so I could simplify.
Yeah, just the evaluations on the trig functions, the small stuff.
Thank you.
Well, looks like we can get started. Welcome back, everyone. So lots of different stuff happened on the Moodle website when we were over on weekend. First thing is we're on week 15. There's really no opportunity to do a homework assignment for the topics we're covering. And so that's why you're going to see for the last 2 sections on volumes by cylindrical shells, there's suggested exercises and reading and the solutions down below. So think of this as the most typical kind of problems you might see on an exam, say the final exam, and same for this set down below here. And pretty much what I'm going to do for the upcoming final exam, since these are the last 2 sections, I'm going to select either 6.2 or 6.3, just one problem using a random number generator, and that's going to be our problem from either of these sections on the final exam. It'll be a pretty typical problem since we don't have a lot of time to practice a bunch of homework examples and have them graded and returned. So if you can solve these problems here or these problems here, you're in really, really great shape for the final exam. Any questions about that so far, folks? Okay, so our goal is we'll finish section 6.2. We might not finish section 6.3 in its entirety, but we'll try to get through the major problems there. And then on Wednesday, when we're finishing on 6.3, we'll convert to reviewing for the final exam. This is the review that I intend to go over. It's pretty long, but we'll kind of cherry pick some of the interesting questions, the tricky questions, those kinds of things as we go through it. So we'll be reviewing on Wednesday and Thursday to close out the week. Then we'll come back on Monday, a week from today, December 11th, from 8 to 10 p.m. in this room will be the final exam. It's a 2-hour exam. You're allowed to have a calculator, page and notes like before. And this is just some advice on how to practice studying for the final exam. I didn't need to change this option right here since I recall that you get to choose your own notes. I copied and pasted this from a different class where they had their notes provided on the exam. So if you go down below, here's the final exams that were from prior semesters. And because we didn't cover we won't cover sections 6.4, 6.5 because of lack of time, I went through all the documents and just said which problem that you could exclude. For example, problem 14, it's either a work problem or average value of a function. That one you could exclude from your studying. Well, any other questions so far, folks? Yeah. It's going to be mainly going through this review right here, but I definitely encourage folks to bring questions to class as well. I'm happy to answer and help out with any questions. So it can be a kind of informal open review. And if we just run out of questions at the start of class, then we'll go to this document as a backup. So if we have a lot of questions and we spend out the day just answering them, that probably could be the best review ever since those will be your questions. Other questions so far? Okay, now, if you take another look at these exams down below, some of them indicate they have solutions and the other ones don't say anything. But if you open up, say, this one, Spring 2018, the solutions to this are on the very, very end. They're kind of abbreviated solutions. They have the answers, not the step-by-step process. But if you want more step-by-step processes, those are the more recent exams, fall 2022, fall 2021. Some of these years were interesting. 2021 was a COVID year, so I think this one was an actual take-home exam. But these ones have the full solutions, the whole process, all the work, stuff like that. By the way, the math department invented this problem. They insisted it was on every single exam in the entire university. This is one we call an assessment question. So this one is not a question that's going to be on the real final exam. Math department just want to know how much we knew about this kind of stuff. So that's what's going on for the reviews down below. And I think I'm just about out of announcements. Yeah, go ahead. It's going to be comprehensive, yeah. It's going to be comprehensive, only going up to 6.3. And I won't be emphasizing, say, one thing occasionally people do, I've done it in my past as well, is exam 3 only went up to 4.7. And so sometimes when people write a final exam, they're going to emphasize 5.1 through 6.3 because those weren't on any of the exams until the final. But for us, pretty much what I'm going to do is treat all the sections as about equal. There's not going to be an emphasis on one section or the other. Other questions about that so far? Okay, and taking a look at the old final exams when you're studying will give you a really good idea of just what a final exam is going to look like. It can't be too long, even though it's 2 hours. It's still, these questions, some of them do take time to get through. And when I write a 2-hour exam, I'm really trying to gun for an hour and a half, 30 minutes built in to just go over the work, double check things, and make sure everything is the way you need it. So there is check time built into the exam as well. Other questions so far, folks, at the moment? Okay, well, let's take a look then at what in the world is going on with the volume section right here. Let me move some of these windows around. Oh, and I forgot to actually open the section. Let me open that as well. That could help. And here we are. This is the penultimate section, 6.2 on volumes. The idea with what's happening here is, suppose, for example, this came out of a different textbook than our own, I believe, but you can imagine maybe it's some kind of bone from thousands of years ago. If you want to analyze this, some of the questions you might have are maybe what is its volume? Sometimes volumes can be very tricky. You may not be able to submerge this and figure out how much water it displaces, especially if it's extremely porous. And so an alternate method of finding volumes is the method of cross sections or slicing. The idea is, if you take a segment here, think of this as a slide, and cut out this little section right here. This would be our cross section. It's going to come in with a width. We can't avoid that if we're doing this physically. The width here, that's going to be kind of hard to draw. Let me draw it this way. The width is going to be delta x. So if you find that width, the delta x goes right here in the approximation phase before taking the limit. Next, we find the area of the cross section. So this area right here, that's our a of x. And that's what's going right inside here. Xi star means we're partitioning from A to B in subintervals, and an I star would just be an ith sample point, although we just showed the cross section here. And imagine as this thing moves for X all the way down to A, we'll have different cross sections as we move all the way down to B as well. But we can calculate the volumes of every single cross section. We just take the area times the thickness, and we have now volumes of these slides. If you let the number of these cross-sectional slides go up to infinity and do the sum of these things, that's now again the limit of Riemann sums. And so the whole thing turns into integrate area from A to B on this diagram, and you will have volumes. So that's a wonderful kind of formula. And we might wonder then, well, what is going on with 6.3? That's also volumes. It just turns out that cross sections don't always work nicely algebraically. Sometimes it's a nightmare, and we'll see what kind of problems where we have to change strategies on. Sometimes this is thought of as the main strategy. It works really exceedingly well when it does work. So the sort of it is, we integrate an area function, we're getting volumes under the right conditions. Any questions about that so far, folks? Okay, let's give it a try then. On our first problem down below, this is about how you might expect your final exam question. I'm going to give the diagrams and things like that since we don't have a lot of time to get through this topic, and it helps us with all the setup as well. I mean, it is a timed exam. A little bit of setup can't hurt. So you might expect this diagram right here where I give the sketch and so on. And what are we doing to this? It says, find the volume of the solid obtained by rotating the region bounded by these three curves. So here's the root x going above. Here's y equals 0, just the x-axis is bounding it. And x equals 4 is the right end bound here. So we have bounded area, and then we're taking that area, rotating the whole thing about the x-axis. So that's what the arrow here is indicating. Rotated this about the x-axis, and you get this picture. Looks like a bullet or something like that, but it's generating out some kind of three-dimensional solid. Our goal is we want to know the volume of this solid. And this is a really, really practical problem. It may not be a bullet, maybe it's some kind of durable medical equipment. And people want to print these out with 3D printers en masse. First question you're going to have is, how much quantity do you need? What is the volume for every one of these devices you're printing out with a 3D printer? This kind of process will tell us the exact values. So that's the problem so far. And the formula is, again, really not so bad. The volume is going to be a definite integral. We integrate from 0 all the way up to 4. So those are the right values for x. Let's maybe highlight from here. Go from 0 to 4. Next thing we have to do is integrate some function we think of as the area function. So integrate a of x with respect to x. So that's our volume right here. But it means the very first step that you really have to take is, well, you need a diagram, pick a typical x from 0 to 4, the valid domain of your diagram, and visualize this, a typical disk or washer obtained by rotating this whole thing about the x-axis. So we need the area of that disk, and its area is a function of x. That's why we write it in as a of x. Say, for example, if x was over here instead, then down below on the diagram, here's where the x is, and our washer would look like this instead. Definitely a different area in that segment. If x moves over to the right, then the area is, well, just going to be the area of this whole entire front face. But we need to know what the area is at every single value of x, as x ranges from 0 to 4. And so we're putting in a whole function that depends on x. So here it goes. First thing we can say is, well, that's a circle. So we're going to use pi r squared for the formula for the area. Area of x is going to be equal to pi times, let's get a new color here. Probably the most important thing is the radius. Try to fix my penmanship here. To the power of 2. So this is the formula for the area of a circle, pi times radius squared. But just like the area depends on x, so does the radius. So now we need to move backwards even another step. Exactly, we get it right off this diagram. And let me put this as another reminder. If this is the question that's coming from the last week on the final exam, this will be provided. So you will have that diagram to work with. From here, that's our radius, the root of x. It comes from the x segment here on the diagram and the upper function right here. So now that we have a radius, this is probably, I would say, step 1 in this process. Unless the diagram is not provided, then we have to provide the diagram, indicate the radius. Then in step 2, drop in the radius so we can calculate the area. So area of x is now equal to pi multiplied by the root of x, quantity squared. Let's simplify that down. Area of x is now equal to pi times x. Power 2 just wipes out the square root, so that's a wonderful function to work with. Then we go to step 3. Plug in your area function and just integrate this new definite integral. So volume is now a definite integral going from 0 to 4. A of x is pi times x dx. It's almost curious in a way that this thing, which looks like it would be a complicated computation just to find a volume, turns into that as a definite integral. Not too much to do left. We just want to find an antiderivative right away. Let's copy in the constant pi to start. give it a little bit of space and power of x bumps up to 2. So now we have to multiply by 1/2 to counteract that power. Integrate from 0 to 4. And we're just skip a jump away from finishing this one off. Any questions at all, folks, to this stage of the process? Okay, let me scroll down a little bit more. Now we are ready to finish this one off. First thing we can do is, let's call this whole constant just a glorified pi/2. It's factored out. And inside where we have the parentheses, we'll put in 4 to start, so 4 squared minus 0 squared. So now it's just pure arithmetic from here on out. This is pi/2 times 16, which tells us this is 8 pi. So if you want to print out this object, say using a 3D printer or something else more fancy, that's how much material you will need in terms of units cubed, whatever the unit might have been, maybe centimeters or something. Well, that's the full process of getting volumes, folks. Usually this is the better 1-step or 3-step process altogether. Start with radius, build area, then just integrate your area to come up with the total volume. Any questions at all? I'm running through this one. Okay, so this one looked like kind of an interesting shape. The one thing that's really a big struggle for me is I'm not artistic. I'm really bad at shading, so I struggle making these diagrams even look believable. You have to have a handle on shading to make that happen. But the good news is you get really everything from right here. And if you can just draw an arbitrary disk or washer, you can get your area formula pretty great. So I usually draw this sketch here, that's provided on the exam, and then I usually draw this thing right here. So let's try this out again in a brand new scenario. We probably don't want to do every single one of those. Let's try to pick out ones that look a little bit nicer. Let's work on our part A on this one to start. And I think there's a typo on this one. No, not quite. Let me double check my list here. Sorry, say again. No, let me double check here. I think I made a change on this one. Yeah, I wanted my second y. Let's hide this list of problems here. Usually I don't type these out and bring them in the notes. I usually bring them here, but I think I forgot to upload the right notes. This one I want to be y equals the cube root of x. Oh geez, where's our cube roots? Oh geez, let's go x power 1/3. Sorry for the weird and random changes on this one. My notes were not quite where I thought they were. So let's do this problem right here. It'll be y equals x squared, y equals x to the power of 1/3, and we're going to rotate this whole thing about the x-axis. Actually, let's read the full instructions to start. We're finding the volume of the solid that's going to be obtained by rotating this region right here about the given curves and specified line. So the line we're rotating about is going to be the x-axis on this one. This is the portion that's going to be provided. We need to sketch the region. We'll try to sketch the solid as best we can and a typical cross-section. Okay, any questions, folks, before we start this one? Okay, let me double check I copied in what I wanted. X squared, cube root of x, about x-axis. Okay, I think we're ready to start. So the trouble with this kind of problem so far is it doesn't necessarily provide even the limits of integration. First thing we have to do before we even sketch this is, for step 1, we're going to equate the right-hand sides, x squared with x power 1/3, just to see what are the right limits of integration. So set x squared equal to x power 1/3. This is kind of a weird equation to work with, but we can get through it pretty quickly by just cubing both sides. So let me copy this step. The reason we want to raise both sides to the power 3 is usually we're eliminating denominators when we're solving equations. So cube the left-hand side and raise the right-hand side to power 3 as well. Said that backwards. Left-hand side to power 3 and right-hand side. So the exponent of 3 multiplies the 1/3 in this configuration, that just turns into x power 1, so glorified x. On the left-hand side, this one turns into x power 6. That's a better equation to solve, but this is a good reminder with equation solving, you definitely don't want to divide by x. Usually you want to get 0 on one side and use factoring. So subtract x from both sides. It's x power 6 minus x equals 0. Then factor is your next step. It'll be x power 5 minus 1. And now that we have two things multiplied together, resulting in 0, we can say this implies x is 0. That's just the first factor, and it's immediately solved. Or x power 5 minus 1 is 0. If you're really good at complex numbers, there's 5 solutions here, but only one of them is a real number. That would be x equals 1. You could add 1 to both sides, take the 5th root, or just plug in 1. You'll get 1 minus 1 for a 0. And so here are the solutions. X is 0 or 1 are the bounds for limits of integration on these two curves. Whew, so we're getting through it so far. Any questions at all, folks, on the equation solving portion? Okay, now that we have the equation, this step right here, again, would be provided on the real final exam. We need to sketch both of these curves and use the limits of integration to help us out. So it's going from 0 to 1. I'm thinking both these curves are above the x-axis, so let's focus on quadrants 1 and 2 this time. We're going from a lower limit of 0 to an upper limit of 1. So we've got those in. Next, we want to plot both of these functions. The quadratic is the easier one. We plug in a 1, we get a 1, and at 0, we're 0. So here's that curve coming in like this. Now the other curve, y equals power 1/3, this one has a different kind of inflection to it. It comes up and around like that. We know it connects definitely on this point and this point because we solved for it when we found 0 and 1. That's where both curves are going to intersect. So this top curve is going to be x to the power of 1/3. Next thing they told us to do is rotate all this about what the x-axis. So the rotation is going to look like this, just to indicate what we're about to do. And this is a moment to make a mention here. If you're rotating about the x-axis, then the 6.2 method for volumes is often most effective. We can mess that up just by putting in horrible curves, making some other method work better. But typically, if it's an x-axis rotation, this would be my first thought. If it doesn't work out, try something else. Okay, so we've got a bounded region right here. Next thing is the hard step. I want to visualize what would happen if you rotated this whole thing about the x-axis. It's going to generate a solid. And that solid might look something about like this. It's kind of hard to visualize, but you can possibly put something out here, something down there to make it look a little bit believable. But I'm always going to leave that up to you. I noticed here it said to sketch the solid, but if you decide to skip that, I'm okay with it. Let's emphasize it here by striking that through. If sketching the solid looks like it's a tough thing for you to draw, but you can visualize it, let's back off a step and just leave it like this. Again, I'll leave it completely up to you. This won't be for credit on the real exam. But the one thing I really would want to plot is a typical disc or washer. So now the limits of integration are going from 0 to 1. That's where this area right here is bounded. Pick a typical spot, just somewhere easy to draw, and call that x. Now, once x is here, a line segment goes up to this location, all the way up to the top curve here. That whole line segment is going to rotate. Let's pause here for just a moment. What I'm trying to visualize right here on the diagram is the same as what I'm visualizing here. That red line segment rotates, generating out a disk this time. Here, it's going to be a washer or an annulus, if you like that word. That's kind of a weird word. So this whole thing is rotating. It means it's also going to rotate down below here. And the whole thing would look about like this. We can find the area of this section right here. We're suddenly in really great business. We can say the entire volume just by integrating that area. So that's kind of a busy diagram already. Let's change it up just a little bit and maybe add some colors. Here's x power 1/3. Here's a y equals x squared. Let me fix that second one. X power 1/3 works, but parallelism helps. Let me make it y equals like the other one. And now here's our x right here. What we're doing is just taking a slightly different point of view. Imagine you're viewing from the x-axis down onto this diagram. It would look about like this. X is in the center, and then the first curve that you would come across on the actual washer would be this one, y equals x squared. So let me draw it in like this. Then it goes all the way up to this curve, y equals x power 1/3. So that one is going to be the blue curve. And they're supposed to be concentric circles, but that's apparently kind of tough today. Imagine that's two perfect concentric circles. The area we're looking for is this area here. We can find that area. Again, we're in really great shape. But to get that area, the next thing we need is the radius as a function of x. So let's call this r of x. And the way to think of this radius is, well, there's two of them. There is a lower radius, and there's going to be an upper radius. So for the smaller radius, that's going from here to here. Lowercase r of x. We can change our perspective on this one and say, it's just whatever the description is for the green curve. And that one is x squared. So the small radius is x squared. Then change gears, and let's look at the larger radius on this one. Larger radius goes from here down to here. Let's call this one uppercase r of x. And because it's going all the way to the blue curve, back on this diagram, we're going all the way to x power 1/3. So we have two radii, I think is the correct plural of this thing. So we definitely need to specify that. And now we're ready for area. Any questions, folks, on getting these two different radiuses so far? Radii, I think is the technical term. Okay, now that we have these radii, go back here, and let's look at the objective of calculating this area. It's not a bad idea to start off like this. Area does depend on x, and if there wasn't this void region in the very middle, we would have said it's going to be pi multiplied by the larger radius of x squared. If you work it that way, you're picking up too much area. You're getting these things as well. Everything is being calculated. So we fix that by subtracting off the radius of the inner circle. So go minus pi times the radius r of lowercase r of x to power 2. From here on out, we're just about done. We need to plug in the right radiuses, square them, and then integrate the result. This is most of the work to this stage, just analyzing the situation, taking a look at the annulus so we can find the right area function. But from here on out, it's not too bad. Let's put in our work. We have pi times uppercase radius is x power 1/3. We'll square that one. Minus pi times lowercase radius is x squared. And then that one gets squared as well. So finally, altogether, we have pi x to the power of 2/3 minus pi x to the power of 4. Now, if we wanted to, we don't have to deal with so many coefficients. You can just take that pi, factor it out, leaving x to the power of 2/3 minus x power 4. So now the claim is, with this method, if you integrate that function, you will automatically get the volume that would have been generated up here in this diagram. I don't know what this would have been, some kind of bowl of some kind, a bowl that would leak because there's a single point here where 3D printer is going to leave a hole for sure. Well, any questions at all, folks, on this stage of the process? Okay, last thing is, really, I'd say the major takeaway. In a certain sense, really the whole purpose of chapter 6 is practice more integration. Probably the more important problem of 6.1, area between curves, is a topic that can come up in Calc 2, Calc 3 in a lot of situations. But these topics here, they're important, they're interesting, but mainly we're just practicing integration when we do 6.2 or 6.3 on volumes. So let's finish out the rest of this. Here's our step 5 to finish the process. We'll write V for volume finally. It's going to be a definite integral. Now we do need limits of integration, but go back to your top diagram. Where you indicated x, we're just putting down the valid places x could have been. It could have been all the way here at 0 and all the way here at positive 1. So we're integrating from 0 to 1. That's the domain of the area function. Now plug in area, it's pi x to the power of 2/3 minus x to the power of 4 dx. And if I thought a little bit further ahead, I would have put this pi in front of the integral sign because it's a constant, but we can leave it right there. Next, find the antiderivative. This is a constant multiplying a function, so nothing happens when we do the antiderivative. It's just pi. Next, we find the antiderivatives of both of these functions, give it a little bit of space and write in x to a power at 3/3, and this becomes 5/3. Multiply by the reciprocal, so 3/5. And that's one term down. We go negative to negative. For the next one, it's x power 5, so we multiply by a fifth. Then back here, throw in the limits of integration and an evaluation bar, 0 to 1. And that's the last bit of arithmetic to do on this. Starting with the upper limit of 1, we'll have pi, I'll go with a bracket on this, times 1 goes here, and doesn't matter how fancy those exponents are, 1 to the power of 5/3 is still 1. So we're just going to pick up 3/5. Likewise, minus 1/5, then minus, and now we're throwing in 0. So I'll just put a 0 minus 0 to say we did it. It kind of looks like a base or some kind, but that's just 0 minus 0 there. So now it's going to be pi times 3/5 minus 1/5. It's already got the common denominator. That's a kind of a nice coincidence on this one. So we get 2/5. Or if you prefer, 2 pi over 5 would be the exact volume of this weird, probably a defective looking bowl if you did 3D print the thing. That's how much material you would need. Well, we did, folks. That's our second volume computation. I think this one is a little bit tricky because of the fact we had an annulus like this right here. If that comes up, this is always the process. Any questions at all in getting through this second one? Okay, these are kind of the main topics that we would take a look at in this section. So I'll leave it up to the class. Should we try a couple more just for practice? Okay, let's try another one then. Again, I kind of did something weird on my notes. I don't usually try to solve every single problem. I usually pick and select a couple of them, but today I put down the actual notes I bring to class. Let me pick out the next one I want to do. I think it was, and I made some slight changes on these as well. Let me call it part B in this way. Part B is going to be a function x equals e to the power of y equals 0, x equals e. And here it says we're going to rotate about the, well, we hope it says x-axis, but this one says y-axis. deserves an exclamation on this one because we just said on the prior problem, the method we just used works really well if you're rotating about x-axis. So the moment the axes are switched and we're still in section 6.2, that's suspicious. We should try something else on this one. But you know what else is suspicious? That function is really kind of weird, right? X equals e to the power y. X is the dependent variable on this one, and y is the independent variable. So the strategy we're going to use on this could be similar to what we saw before. Let's take a look at 6.1 just for the moment. In 6.1, all we wanted was areas between curves. And this is the standard kind of problem. This one's not too bad. Here, x is the independent variable in both of the functions, and y is the dependent variable. So we just went from 0 to 2, took the upper curve minus the lower curve, and integrated. But the problem we're doing is more similar to this problem. Sometimes the role of x and y has just been completely flipped on us, like on this diagram right here. Whenever that happens, it may not be a bad idea to literally change your roles of x's and y's. Integrate with respect to y, so a dy would go here. And the whole problem might be far, far easier just all of a sudden. Here, this one, we try to solve for x and do it directly. It wasn't as bad. Here, it would be really, really bad. This is a terrible problem to go at directly unless we change our point of view on this one. So here's how we can start to visualize this. It's x equals e to the y. That's an interesting thing to plot. Well, let's go right to the diagram. Don't necessarily know where things are going to end up, so let's just put all coordinates there equally weighted. And plotting x equals e to the y, you might start off with this strategy. If x is equal to e to the power y, take the natural log of both sides, and you get natural log of x is y. And to me, that function is a lot easier to plot. Y equals natural log x. You have some nice key values. One key value is always 1 in a logarithm. Natural log 1 is immediately 0. Next nice value might be e, since natural log e is 1. And from there, we can plot that function, x equals e to the power y. So first point is going to be 1, 0. Then here's 2, here's 3. And this point of e is about 2.7. And about 2.7, we take a height of 1. So we're over here for a second point. Then the rest of the curve would look about like this. This time I'm drawing just the whole thing because I don't necessarily know what the bounded region is. I don't know if it's above, below, left, or right. We have to work on this a little bit and discover where everything is going to fall. But this is x equals e to the y, at least. We have 1 down. Next curve, y equals 0. That's just the horizontal line going through the x-axis. So it's going, I mean, it's kind of there already, but I'll put another line just to emphasize it. It's somewhere over here. So now we have one more, x equals e. E is about here, and that causes our vertical line segment to go through like that. Suddenly, we have a bounded region. It's right exactly here. So that whole region is rotated this way, about the y-axis. A little bit annoying, but we can deal with that. Okay, so we're through the first battle of this thing. We had to provide our own region. Now, when we rotate this, we need to pick a typical value, but keep in mind, we're also changing our way we're viewing this whole problem. We're thinking of y as the independent variable, and valid choices for y would be 0 to start. That's as low as it could go. Let me highlight this just to help with the visualization. So y could be as low as 0, or it could be as high as 1. Let me actually just write this as 0, 1. Kind of weird to put the variable there. The actual y value can only be between 0 and 1, so let me plot it right here. Here's a typical value of y. Whole thing is rotated about the y-axis. And so one thing that also rotates is Let's take this y, go to the right until we hit the curve right about here. Carry down a line segment until you hit the boundary right over here. And this whole thing is going to rotate on us. Probably good time to indicate a little bit more information. Let me take x equals e to the y. I mean, it's okay over there, but let's emphasize it here. There's x equals e to the y, and this curve where the area stopped, this is x equals e. So the way we're viewing it is left to right. So think of y as being anything from 0 to 1. Everything's rotating, including this portion. Let me kind of attempt to mirror it on the left. We get that segment, and now we have another washer. So from here to here is the outer radius. The inner radius is this smaller circle right here. And like before, if we can find the area of this diagram, we're in really, really great shape. Any questions, folks, with what we wrote out so far? Okay. Well, again, you can take this diagram right here and revisualize it as a whole different set right here. But if the work doesn't look too busy, let's see if we can put it in right now. First thing will happen is when we go here to here, we're going to hit this portion of the curve, x equals e to the y. So that's going to be our lower one, our inner radius. So let's call this lowercase r of x is going to be the segment here we put in blue. And I already made a mistake, darn it. I called it r of x. That's not right. We're plugging in a value of y, and y goes from 0 to 1. So over here, I should have wrote r of y instead. Let's backtrack on that. It's kind of strange changing your point of view. X's and y's changes roles. But here's one side effect. It has to be y here for our function. When we come over here, we hit the inner radius, and the function is e to the power of y. So there's our inner radius. Next one goes like this. We extended all the way out here to that length. We're going to hit the outer radius, but that one's not so bad. That one's a constant function. It makes sense wherever y is, move it up or down, this line segment always stops right at e. So we'll say the upper radius, r of x, e no matter what. It's just a, or sorry, say again? Oh yeah, absolutely. Thanks for spotting that. It's a terrible mistake to make twice in a row. R of y again is always equal to e. Thanks for spotting that. So now that we have the two radii, however we want to say it, our next goal is to get this area. Hardest thing about this is to draw a diagram that gives us the information we want, visualizes the problem, and doesn't get too busy so we can't tell what's going on. Does that look okay to folks? It's not too busy just yet. Okay, so here's our next step. The area, almost did it, area at y, let's just change that curve a little bit in the middle, is going to be pi multiplied by the larger radius squared. So pi r of y, quantity 2. Then find the lower area, pi times lower r of y, power 2. Next, plug in the functions. And the first one's going to be pi times ordinary e squared. It's kind of convenient and nice. Then next one is going to be pi times, let's look up r of y. That one came out as e to the y. And we're also raising that to power 2. So let's do a new line. Area is going to be, we factor out pi from both like before. That's just for slight convenience, makes the rest of the problem easier to write out. We'll be left over with e squared from here, minus e to the power of 2 times y coming from over here. This is kind of a tricky integration. The first one's a constant, so when we integrate it, we just hit it with a variable. And the second one is not constant, and it could be thought of as a u substitution type of a problem. So think of this next step, really we're just reviewing for the final exam right at this stage. So we'll say that the volume will be from this wedge region rotated all around. This would look like some kind of weird ring of some sort. It's a definite integral as y itself goes from lower limit of 0 to the upper limit of 1. So 0 to 1. We throw in this function, pi e squared minus e to the power of 2y. And we're integrating with respect to y, so we throw in dy. Finally, that's our integral to solve. If we can get a quick antiderivative, we'll be home free. Well, we need an antiderivative of e to the power 2y, so it's not a bad idea to just do that on the margin, and so we can, and then finish out the rest of it. So let's take a slight pause on this problem. Go over here, and let's integrate e to the power 2y. I wrote this one out as just an indefinite integral. All I'm going to produce is an antiderivative, and I'll plug it back here where it's now a definite integral. Now, like we mentioned before, it is a U substitution problem, but when you get into Calculus 2, a lot of U subs are just done right on paper mentally. So let's try it both ways. Let's try to guess an antiderivative. We'll fine tune it until it's the right one. And then for the sake of review, we'll do the U substitution for folks that prefer that method as well. They're both just as valid. So if you were going to guess an antiderivative of this, well, we do know the derivative of a base E exponential is itself. So I'd probably start with e to the 2y to start. There's going to be a constant at the end, but I left a little bit of space because I'm not expecting this to be exactly right. Something's got to go there to make the derivative come out correctly. Anyone spot what the constant would be? It's not 2, but you're very, very close. It'd be 1/2 exactly. And here's how you might visualize this. The moment you wrote down e to the power 2y, visualize differentiating it. Let's do it on paper down below. If you differentiate that, it's a chain rule. First thing you do is copy e to the 2y. And then you multiply by the derivative of 2y, which would give us a 2 right here. So it's 2 e to the power 2y. This tells us that's not the right derivative because that's not the right antiderivative because when we differentiate it, a 2 comes out and there's no 2 inside here. So we counteract by putting in a 1/2 and suddenly that's the right answer to this one. So we're going to plug in 1/2 e to the power 2y. We'll leave off the constant because we just need any antiderivative here, the definite integral. Well, this is doing it visually. We just put down the answer. But as promised, this is Calculus 1. We're expected to do these by U substitution as well. This is just what's going to happen in the future. A lot of these are just kind of written in this way. So let's do the U substitution below, and then we'll finish off the problem. So let's put it maybe right over here. If you're doing e to the 2y dy, and you don't want to take this approach of just guessing a value and coming up with the right thing, then we need to pick a u. Any volunteers in the class for a good choice of u? Good call. This is where I would always look. Look for something that looks like an inner function if you were differentiating it. Now, we're not differentiating, we're doing an antiderivative, but 2y is still inner there. Once we have that down, we need the full differential of this thing. The left-hand side is du. Here, the derivative of 2y is just a 2, and the right-hand side will be dy. That always looks weird, but remember we changed x's and y's, so dy is on the right-hand side now. 2 is missing, and that was the same problem up here. 2 is missing in that location, so we just divide it out. Here's a 1/2. du equals dy. And this highlights finally why this shortcut's taken so much. Dividing out the 1/2 is the same exact thing we did up here. Down below, we're just doing it with lots of extra steps to see it in a different way. So this whole dy is replaced with 1/2 du. The 2y is replaced with u, and this turns into First, I'll throw in the half. That should have been in blue, just to carry the color coding down. There'll be e to the power of just a u, and then a dy, excuse me, a du. And so that's our full substitution. So dy split into 1/2. We chucked it out since it's a distraction sometimes inside. Du went to the left, to the right. Next, this antiderivative is much easier to do. We're going to get 1/2 antiderivative of e to the u is just e to the u. Add a constant. Next, undo that substitution and we get 1/2 e to the power of 2y plus a constant. So that's done two different ways, and really it's important to see it both ways. I'm mentioning these a lot because in Calculus 2, it becomes more of an expectation. So our goal is to understand the u substitution well enough to just do it on paper like this. But going through these motions, that's how we get there. So this is the main thing we emphasize in Calc 1. Well, we did it, folks. It's easy to forget what we were trying to do in the first place. Back to the volume problem. We're trying to solve that. What we found was an antiderivative, so we could put in pi to start from the constant multiple rule. We need an antiderivative of e squared. That one's tricky. Anyone see what it should be? Exactly, yes. E squared, think of it like 5 as a constant. It's 2.7 to power 2. It's about 9-ish, a little bit less. And so here we'll put in e squared. And good call on that one. The variable is y because we're integrating with respect to y from this dy here. So e squared y. Then on this one, we found an antiderivative. So on either spot, carry it in. I'll think of it this way. It's the same stuff either way. Plus, oh, hang on, minus is what we had in the middle. So minus 1/2 e to the power of 2y. Then we are evaluating from 0 to 1. So that's our whole process. We just have to crank this out next. Any questions so far, folks, on this strategy so far? Yeah. Oh, so that one came from integrating this right here. Let's do that on the margin. Let's think of this one as kind of by analogy. That one is extremely tricky, but if it looked like this, it wouldn't be as bad. It's a constant either way, right? So over here, antiderivative of just 5 would have turned into 5 times x. Or, hang on, I made a mistake. It's a dy, so it's 5 times y, rather. Plus a constant. Over here, if it's e squared, same strategy, we just have to multiply it by y. Does that make sense at the moment? Yeah. Gotcha. Other questions so far? Okay, all we've got to do now is throw in the limits of integration. So this is turning into pi times. One goes in the position of y, so we'll get e squared minus 1/2 e squared. So that's our first step. Then a negative sign goes in. It's a good idea to put in another set of parentheses as we're throwing in a 0. We'll get e squared times 0 minus 1/2 e to the power of 0. And I'm noticing a lack of space here, so I'm going to use the strategy of arrows. You have a page break. I try to avoid those, but it happens. So it continues down. We just have to crank all that out. So the first one is 2 over 2e squared minus 1/2 e squared. So you can consolidate those like terms and call it just positive 1/2 e squared altogether from the first two terms. This is being wiped out. It's equal to exactly 0. And this is equal to negative 1/2. So it'll be plus 1/2 after distributing. And, you know, I don't know if we'd want to take it any further. This looks like a pretty decent answer just as it is. If you wanted to make it look slightly cleaner, you could factor out 1/2. Call it pi over 2 times e squared plus 1. So that's our total volume of this region when it's rotated and generates a solid. Does that look right to folks on that end answer here? Okay, So we did it, folks. That's dealing with volumes. I feel like these questions here, the last two that we did solve, they're not too bad as an exam question. But the one thing I feel like is a little bit overreaching is the annulus right here. I think that's a little bit much for a brand new topic that's going to be a week away in an exam. So the way this might look like on a real final exam is, once again, something about like this, where this diagram will be provided to help out with the setup. And the main takeaway on all these sections is we're just trying to practice integration. So once we get down to here, this is the main takeaway of all these sections so far. Well, this section is now complete. I don't think we have enough time to start off a brand new problem. They're pretty long. But on the suggested exercises and the homework here, these won't be collected, but you could take a look at these right out of the book. And I have the solutions posted down here. You know, one thing I did forget is not everyone has the book. I've been posting the exercises since people might have old editions. So I'm going to also post the actual exercises. I think I forgot to do that. Post the actual exercises for 6.2, 6.3. So that's what we'll do next. So this will be our last section when we come back on Wednesday's class. Just to give you a visualization of what's happening, this is a method that's really good if we're rotating about the y-axis, and it does not make sense to interchange the roles of x and y because we don't have functions given in this way. We're going to use the method of cylindrical shells, which is a wild method. Here's what it looks like. You take a curve like this one in blue, it's going to be rotated about the y-axis, and this is where the method shines. A y-axis rotation says cylindrical shells is probably your best bet. So rotate that bounded region, and here's your solid. There's really good shading here. It looks like a believable object. To find the volume of this, we construct cylindrical shells. This whole thing is rotated. They look like this, and we can find the volumes of those shells by this formula above. That means break it all up into a bunch of cylindrical shells, and you get this stuff. That's, well, a Riemann sum. So if you take the limit of a Riemann sum, part of our work in chapter 5 is to say it transforms into a definite integral. It turns into this right here. So if you are using the method of cylindrical shells, what we need is a shell radius. The radius is going to be the distance from this x all the way to 0. So sometimes it's just x itself, and the typical problems will solve. You'll need the shell height. The shell height is just the function itself going through right here. Integrate all that, and you're done. You have the volume of something rotated about the y-axis, where it's not done in this funky way of changing the roles of x and y. Sometimes that's not a good way to go, depending on how complicated the functions are. So when we come back on Wednesday, we'll practice a couple of these problems. I don't want to take up too much time in this section, since we also want to change gears on Wednesday and start reviewing for the final exam as well. But any questions, folks, with where we're at so far? Okay, I don't think we can solve one in the amount of time we have, so we'll come back fresh, give these new problems a try, and we'll do this thing right here, except it's going to be rotated, this time not about the x-axis, which made it look like a bullet. We're rotating about the y-axis and see now what do we have to do to make this work out. Well, have a great night, folks, and we'll meet again on Wednesday, right here on example 1. Hey, questions?
Yes. I have a question on this one right here.
Mm.
So I joined it together, but then I don't know where to start because I have to find the other one.
Gotcha. Well, looking at this problem so far, one thing that kind of just pops out at me is if you're doing natural log x squared, and it's minus a natural log x, you can actually consolidate both of these into one and go natural log. The negative right here turns into a division. X squared goes on the top. This x goes on the bottom. And it turns into just natural log x altogether.
Okay.
So if you went that route, here's another portion of the notes you might want to look at. It's in, I think, 5.3. I think it's in 5.3. Let me try again. Maybe 5.4. So in section 5.4, there's actually a kind of nice formula provided. Antiderivative of the natural log is all this stuff right here.
Okay,
So you could put in antiderivative, that's an integral sign drawn badly, sorry about that, equals x natural log x. Then it's a minus x plus a constant. You won't need the constant, or I forget what's going on with this one. Was this one, oh, you're doing an area, so yeah, you wouldn't
Yeah.
need the constant on this.
okay,
So that will get you through this problem right here.
okay. And then that'll help me find the other one that goes on here.
Oh, for that, finding the limits of integration, that's kind of a different setup. You'd have to take natural log x, set equal to natural log x squared. But then we'd use the same approach, subtract natural log x from both sides. So you would have 0 equals natural log x when we simplify down to that step.
Okay.
So you'd have to solve that equation.
Okay,
And solving this one, you can take and write e to the power 0, e natural log x. E to the power 0 is 1, and you get a x equals 1.
so it'd be as 1 to 2.
1 to 2 on this one, yeah.
Oh, okay. Okay, that makes sense
Awesome. Do you
now.
want this up
Yes.
first? Here you go.
Okay,
Cool.
and so that's what I would do on number 9 as well.
Yeah, set them both equal to each other, and
Okay.
you'll get 2 limits of integration on that one.
Okay, thank you.
Yeah, absolutely. Sure.
Know if the book using Calc 2 is the same one they're using.
It is the same one,
Okay,
yeah.
so I don't like spell back or anything.
You do not know. Yeah, that's one thing that's nice.
Yeah.
They used to sell a book this big, which was Calc 1, Calc 2, Calc 3, and that was nice, except by Calc 3, it started to fall apart a little bit.
Yeah, so it's, yeah, same book.
Same book, yeah.
Thank you.
Mhm.
We can get some Calc 3.
Calc 3, they have just a smaller text about this big. It is the same one, but they separated the texts. Yeah,
So wait, so by the time you did Calc 2, then you will not full book.
you'll have to buy a Calc 3 book if you're going into Calc 3. That's the downside. They used to just sell one text. I think I paid $250 for it. It's terrible. And it worked for 3 classes. Now they've got 2 texts. Calc 1, Calc 2 is one text, and Calc 3 is another one. Mhm. Yep, you betcha.